This video is brought to you by mywayteaching.com.
Now let us study law of equipartition of energy. The kinetic energy of a single molecule is given by one by 2 m vx square, the component of velocity in x direction, in y direction as well as in z direction. Isn't it? Vx, vy, vz. This is the velocity kinetic energy of a single molecule. For a gas in thermal equilibrium at temperature T, the average value of energy is given by average value of energy is given by 1 by 2 mvx square plus 1 by 2 mvy square plus 1 by 2 mvz square is equal to 3 by 2 kb into t, isn't it? Since there is no preferred direction, this equation implies one by 2 mvx square is equal to 1 by 2 kb into t. Similarly, 1 by 2 mvy square is equal to 1 by 2 kb into t, and similarly 1 by 2 mvz square is equal to 1 by 2 kb into t. Okay, a molecule is free to move in space. It needs three coordinates to specify its location. If it is constrained to move in a plane, then it needs two. If it is constrained to move along a line, then it just needs only one coordinate to locate it. Isn't it? Yes, this can also be expressed in another way. See, we say that it has 1 degree of freedom for motion in a line. Okay, which means it requires only one coordinate to represent its location in a line. 1 degree of motion. Isn't it? 1 degree of freedom for motion. In a line. Whereas in case of plane, 2 for motion in a plane and 3 for what? Space, isn't it? Yes. Motion of a body as a whole from one point to another is called as translation. Okay, motion of a body from one point to another as a whole. As a whole, it is called as translation. Okay. Thus, a molecule is free to move in space. It has three translational degrees of freedom. Each translational degree of freedom it contributes a term that contains square of some variable of motion. For example, half mvx square, and similarly for vy and vz, isn't it? As we just saw in the equation. In thermal equilibrium, the average of each such term is given by 1 by 2 kb into T. Okay. See, molecules of the monoatomic gas means which contains a single atom, monoatomic gas like argon, they have only translational degrees of freedom. But in case of diatomic gas such as O2, N2, in what happens in that particular case? Yes, in that case, a molecule of O2 it has three translational degrees of freedom, whereas in monoatomic gas it has only translational degrees of freedom. In case of this O2 N2, it has three translational degrees of freedom. But in addition, it can also rotate about its center of mass. So it is also rotational, not only translational. So you can see in this figure, it shows two independent axes of rotation, one and rotation two, normal to the axis joining the two oxygen atoms about which the molecule can rotate, isn't it? Two independent rotational axes. The molecule thus it has two rotational degrees of freedom, isn't it? And each of which contributes a term to the total energy consisting of translational energy, and even it contains rotational energy. Translational energy and rotational energy. Okay. So here we can write that total energy as, we can write it as epsilon r rotational energy plus translational energy, that is given by this is rotational. Okay. Okay, here W1 and W2 are angular speeds about axis 1 and about axis 2. I1 and I2 are the moments of inertia, isn't it? Okay. And here each rotational degree of freedom contributes a term to the energy that contains square of a rotational variable of motion. See here we have assumed that molecule, that is O2 molecule, is a rigid rotator, that is the molecule does not vibrate. Even though this assumption is true for O2, but it is not always valid. Sometimes it vibrates. Like molecules like carbon dioxide, even at moderate temperatures, they have a mode of vibration. Its atoms oscillate along the interatomic axis. Okay, like a one dimensional oscillator, and they contribute a vibrational energy. That vibrational energy term is given by non B. This is vibrational energy term, and this energy is also added to the total energy. So it is given by 1 by 2 m dy by dt square dy by dt the whole square plus half ky square. So that total energy will become the sum of translational energy, rotational energy, and vibrational energy. Here, okay. So here this K is the force constant of the oscillator, and Y is the vibrational coordinate. Okay. So here that vibrational energy term, it contains square terms of vibrational variables of motion, that is y and dy by dt. Here, isn't it? You can see here it contains these square terms. See in this equation, while each translational and rotational degree of freedom has contributed only one square term, isn't it? In equation that means this one, equation 1, let us consider in this one vibrational mode contributes two squared terms, that is kinetic and potential energies, whereas this translation and rotation only one square terms, but this vibrational it contributes two squared terms, that is kinetic and potential energies, isn't it? So each quadratic term which occurring in the expression for energy is a mode of absorption of energy by a molecule, which means in thermal equilibrium at absolute temperature. Okay, in thermal equilibrium, that at absolute temperature T, for each translational mode of motion, the average energy is equal to 1 by 2 kb into T. That is true. A most elegant principle of classical statistical mechanics states that this is so far each mode of energy, that is translational, rotational, and vibrational. translational, rotational, and vibrational. Okay. That is, in equilibrium, the total energy is equally distributed in all possible energy modes, with each mode having an average energy equal to 1 by 2 kb into T. This is known as law of equipartition of energy. So, the total energy is equally distributed in all the possible energy modes. Okay, that's what we call it as law of equipartition of energy. So each translational and rotational degree of freedom of a molecule contributes 1 by 2 kb into T to the energy, while each vibrational frequency contributes 2 into 1 by 2 kb into T. Since a vibrational mode has both kinetic as well as potential energy modes. Okay.